Very good evening, my dear students. Welcome to ACE Engineering Academy. It's a ACE Preparation Strategy League Season 2. Now, introduce myself. I am A. Ravinder Reddy, the Faculty of Mathematics Department in ACE Engineering Academy. Today, we are going to discuss about the preparation strategy, some important concepts and problems of or most frequently asked problems of the complex variable topic only. So today's topic is complex variables. Okay. Now let us start the slide. The complex variable topic is one of the subtopic of mathematics part. It is there for all branches except civil gate examination. Earlier it was there for civil also. Right now it is not there. The complex variable topic is not there for civil gate examination only. Civil branch of gate examination only. And CSC branch of the gate examination only. It is there with the EC branch. EC means electronics. Next electrical branch, mechanical branch, instrumentation branch. For production branch. For all these branches it is there, but for CSC and civil branch of gate mathematics it is not there only. Okay, but in IES prelims examination this complex variable is there for all branches only. So it is required for IES and also the gate examination. Now let us consider the subtopics of this complex variable according to our gate syllabus. These are the subtopics. Very first one is analytic functions. Second one is complex integration. Third one is complex power series. And the fourth one is complex integration. The second and last are same, complex integration, complex integration. Here, the complex integration without residues. Here, complex integration using residues only. So both are same, without residues, with residues only. For residues, we require the complex power series only. Okay. From the power series, we try to write these residues, and using residues, we evaluate the complex integrals only. Now, these are the references or reference books for this complex variable. Many are there, but here I took the three. One is ACE Academy material. ACE Academy material. Next, Advanced Engineering Mathematics by SRK Iyengar, RK Jain. Next, Complex Variables by Jain Sharma. But our material is confined to the syllabus of the gate examination, and these are the books, standard books. We can find the complex variable topic in the books, but beyond the syllabus only. We can consider the extra topics also in this, but according to our syllabus, we have prepared this material, so we can follow this material. If you have any doubt, then go to the standard books only. Otherwise, just the S material is enough for gate examination and IES examination. These are the references. Now, coming to the preparation strategy only. For any entrance examination, the time is important. Okay, so we should be given a limited time. In that limited time, you have to answer more number of questions only. So for this, we should follow some preparation, or we should have some preparation strategy only. Now, the first, let us consider the class notes. Refer the class notes only. The class notes is important only. If you are online class student, or if you are offline class student, or anything only. First, go through the class notes. First, go through the class notes only. Okay, the class notes is very, very important. After completion of any class, any subject or any topic of the class, after completion of any topic, okay, first go through that class notes and try to practice the classroom questions, whatever the problems done by the faculty in the classroom. Okay, if it is offline or online, first try to practice the classroom questions twice or thrice. Twice or thrice. The practicing the twice or thrice is important. Once practice twice or thrice, or based on the time, you can practice more number of times also, 4 times, 5 times also. After practicing all these questions, then refer the coaching material also. That is also important. Next, while practicing the questions, in the classroom, while practicing the classroom questions, whether it is offline or online, whenever you find the formulae or properties, okay, while practicing the problems, whenever you find the formulae or wherever you use the formulae and properties, try to write all the formulae, properties, and together, all the properties and formulae together at one place, so that we can refer directly the properties and formulae also later also only. Okay, frequently we can use some formulae and some properties only, so we can get all the things at one place only. If you write all the properties and formulas at one place only, that is very important only, because mainly we focus on formulae only. Okay, if you know the formula also, we can go through that one. Next, we require the coaching material also. The coaching material is also important, okay, because that is confined to the syllabus of that entrance examination. That is why that is material is important only. Okay. Next, after the completion of the practicing the questions in the classroom, okay, we go to the previous year's question papers of different examinations only. If you are preparing for GATE examination or if you are preparing for IES examination, try to collect all the question papers of that GATE examination and IES examination. And for GATE examination, we have 30 years previous years question papers. For IES, we have the 6 years previous years question papers only. Like that, you can collect the DRDO examination questions, BARC examination questions, ISRO examination questions, and public service, that is PSU examination questions papers. If any examination is related to your syllabus, then try to collect all the question papers and try to practice all the question papers, the previous year's question papers questions only. The practice in the previous year's question papers is very important, because you will find the similar model questions only. You take any topic, in each topic you will find the limited number of problems only, limited number of models only, limited number of models, that is finite number of models only. So after completion of all the models, after some years, what do? You will get only same thing only. So that is why the practice in the previous year's question papers is very important only. You take any topic or any subject only, whether it is core subject or non-core subject or anything only, for any entrance examination, collecting the previous year's question papers and practicing the previous year's question papers is very important only. Okay. So once you practice the many model problems and many times, then you will master in that only. And also you get the fastness only. The fastness is very important only. Because for entrance examination, the time is crucial only. The time is crucial only. You will be given a limited time only. In that limited time, you should answer more number of questions only. So to answer more number of questions, you should have practice before the examination only. For practice, you should sit more number of hours. For sitting more number of hours, you should have patience only. The patience is also very important. You should not lose the patience at any stage only. If once you have patience, you can sit more number of hours. Once you sit more number of hours, you can practice more number of questions and more number of times only. So the more you practice, the more you can answer the questions in the examination only. So practice. That's all. It's only the practice is the shortcut for success only. Okay. For writing entrance examination, the shortcut is, if anyone asks shortcut means, the shortcut is only practice only. So for this, we require the patience. So patience and practice, these two are the main things only. Okay. So practice many times. That's all. Nothing is there only. Already you know all these things only. You will study same thing in your BTech. Also you will study again same thing here also. The thing is only the practice only. Knowing the method, knowing the problem is not important only. Once you understand the concept and once you understand the theorems, results, properties and everything, you should have practice after that only. Knowing is not important. First you should know and understand, and after that you should practice only. Once you practice only, then you get the perfectness only, and also the fastness only. If you practice many times, then we get the fastness. So with that fastness, we can answer more number of questions in the examination. So practice is very important only. Okay. And revise as many times as possible only. So practicing only 1 time, 2 times, 3 times is not important. Practicing the many times is important only. Practice many times is important from here onwards till examination only. Is it clear? Or you can follow this. Suppose if you start the preparation today, any topic or any subject, first you should start today, and then you have to repeat the same thing within the 24 hours. Whatever you start the preparation today for anything, any topic or any subject, you have to repeat the same thing within the 24 hours. That is important only. Repeating the same thing within the 24 hours is important. And again, you have to repeat the same thing within the 1 week. 1 week. After that, again, you have to repeat the same thing within the 1 month. And then you have to repeat the same thing within the 6 months. Okay? Once you start any topic today for preparation, then you have to repeat the same thing within the 24 hours. And then you have to repeat the same thing within 1 week. And then 1 month. After that, within the 6 months only. So that we can remember up to 1 year. Okay? So this is very, very important. This is according to psychology. So you have to prepare like this only. And also, depending on the person, you may require more number of times also than this only. So here onwards, you require the 6 or 7 or 8 times practice only. The practicing is very, very important on that. Okay? That is a revise. And try to attempt all the test series. Try to write all the test. Try to write all the test only. Here we connect the topic-wise test, next subject topic-wise, each subtopic-wise test, and next the mock test, grand test, like this on subject-wise also. Okay, first topic-wise, next subject-wise, and then the mock gate test on. So try to practice all this. Try to practice means try to write all the examination. Don't skip that only. Practicing the means writing the examination is the practice on here on. Try to attempt all the test series only. Once you attempt all the tests, you will have some experience before the examination only. So without practicing the test, directly if you go to the examination, you may not do all the questions only, many questions only. So practicing all the questions is very, very important. That is why before the examination, try to practice or try to attempt all the practice tests only. Okay? Once you practice like this test, or if you write the test before the examination, you will have some experience on it. After practicing all the questions in the classroom, if you go through the previous year's question papers, and if you practice that only, you will get a lot of confidence only. And you will know how the questions will come, whether you are able to do the problems or not only. Okay? So practice is very important, the previous question papers questions only. So like this, if you follow this strategy, we can answer more number of questions, and also we can prepare well without any fear. We can write the examination. Okay. So first you have to build. The confidence. Once you build the confidence, and if you have a confidence, freely we can write the examination without any fear on it. Right. So this is about the strategy only. Now let us go to the topic, complex variables topic. Already we have seen the subtopics of complex variable topic. The complex variable topic is one of the subtopic of mathematics. In mathematics, we have many topics: the linear algebra, calculus, differential equations, probability and statistics, numerical methods, Laplace transform, and complex variable. So out of all this, one of the subtopic is complex variable. So today we have taken that complex variable topic. In the complex also, we have the many subtopics: analytic functions, complex integration, next complex power series, and complex integration by residues only. So out of all these, we have taken here the complex integration. Why I'm choosing this complex integration means here, if we go through the previous year's question papers of GATE examination, we can find that most of the questions on this topic only. If you observe all the 30 years papers, most of the GATE questions were given on this complex variable topic from this complex integration subtopic only. Most of the GATE questions were given on this complex integration topic of this complex variable topic only. That is why today I took this complex integration topic only. Now in this complex integration topic, first we'll discuss about some definitions. These are some definitions: neighborhood of a point, next analytic function at a point, singular point, entire function. So before going to do the problems on complex integration, or before going to discuss the method of evaluation of complex integration, first we should know how to check the function is analytic or not, or what is the meaning of analytic function. Next, the definition of singular point, when do we say that the point is singular point, when do we say that not a singular point like this, and also we should know the entire function. So these things are important. Once you know this, we can go to directly the complex integration topic because we require all these only. So let us start with the first definition, neighborhood of a point. Neighborhood of a point. The name itself is the neighbor. Neighborhood of a point means we collect all its neighbor points on it. We collect the neighbor points of that point Z naught only. First of all, we consider the complex plane. Complex plane is a two-dimensional plane. This plane region, it is a real axis, it is the imaginary axis, or this is the x-axis, it is a y-axis only. Every complex number can be chosen on this plane region only. Every complex number can be chosen on this plane. In general, we write the complex number as z equal to x plus I y. Or we can write the same complex number in other form as a ordered pair of two real numbers or as a coordinate of a point x comma y like this only. So we can write the complex number like this z notation, z equal to x plus I y equal to x comma y only. Every point on this is a like this form. Now, in a complex plane, let us consider the one point. Let us consider one point, Z naught, and we collect all its neighbor points or surrounding points only. We collect all its neighbor points only. I can take this as neighbor point. Someone can take this as neighbor point. This as neighbor point. Someone can take this as neighbor point. Not like this only. All are neighbor points only. Like this, we cannot choose the neighbor points. Randomly, we cannot collect the neighbor points only. So to choose the neighbor points of this point, there is a condition. The condition is distance only. First, we should fix some distance. Within the same distance, in radial direction, we collect all the points only. Let us consider the distance like this, d distance, d units distance only. Within the same distance, in radial direction, in all directions, we collect all the neighbor points only. In this direction, this direction, this direction, in this direction, like this. In all directions, in radial direction, we collect all the points within the same distance only, Okay. Take a point, fix some distance, within the same distance, collect all the neighbor points, It is same as the circular disc, the plain circular disc only, open circular disc only. Or otherwise, we can say this like this, Z naught point, take a distance d units and draw this circle. Within the circle, collect all these points. The collection of all points within the circle having center at Z naught is the neighborhood of a point only. So collection of all its neighbor points within the distance d is the neighborhood of a point. It is also same as the taking a point, fixing some distance within the same distance, collecting the point means collecting all the points inside the circle with center at Z naught. Collecting all the points inside the circle with center at Z naught. So collecting all these points in this region, in this plane region, circular region, is the neighborhood of a point. So neighborhood of a point means the collection of all its neighbor points in a plane region only. And it is denoted by like this, capital N suffix d, after this within the brackets Z naught. It is a collection of all points. So within the set brackets, we write the Z colon modulus of Z minus Z naught less than d only. So the collection of all points satisfying this inequality is the neighborhood of a point. That is, take a point, fix some distance, within the same distance, collect all the points only. That is a circular disc only, or collecting all the points inside the circle with center at Z naught. This is about the neighborhood of a point. Next, analytic function. Next, we'll discuss about the definition of analytic function at a point Z naught. At a point Z naught. we consider the complex function w equal to f of z equal to u of x comma y plus I into v of x comma y. We have taken the complex function w equal to f of z equal to u of x comma y plus I into v of x comma y and the point z naught, Here, two conditions. The first condition is, at this point z naught, derivative of this function should exist only. The derivative of this function should exist at this point z naught. And the second point, in the neighborhood of this point, z naught also, at every neighborhood, at every point of this, at every neighbor point of this also, the derivative should exist only. At a point z naught, derivative should exist. In the neighborhood of this point also, at every other point also, derivative should exist only. It is a condition. Okay. At a point z naught, derivative exists. At every neighbor point of this point z naught is also derivative exist. Then we can say the function is analytic at a point z naught only. At a particular point, if you want to say that function is analytic or not, at that point, first of all, derivative exists or not, check it only. Once derivative exists, then we consider second condition. What is the condition? In its some neighborhood also, at every other point also, derivative exists or not, check it only. So at a point z naught, derivative exists. At every other point also, derivative exists. Then we can say function is analytic at a point z naught. That is, first of all, derivative exists means the function is called differentiable. Whenever derivative exists, the function is called differentiable function only. So from this we can say the function is not only differentiable at a point z naught, the function is not only differentiable at a point z naught, but also differentiable at every other point in some neighborhood of a point. The function is not only differentiable at a point z naught, but also differentiable at every some point, at every neighbor point of some neighborhood of this point only. Function is not only differentiable at a point z naught, and also differentiable at every other point in the some neighborhood of a point z naught only. Right? That is, at a point z naught, derivative exists. At every other point also, derivative exists in its neighborhood. Then the function is said to be analytic function at that point, at a single point only. Suppose if you consider some region like this. This is a plane region. This plane region contains many points only. If you want to say that function is analytic in this region R, just now we have discussed about the analyticity at a particular point only. Suppose if you want to discuss about the analyticity in the region, in this region, at every point also the function is analytic. It is a plane region. This plane region consists of many points. At every point of this region, the function is analytic. Then we can say the function is analytic in the region R. Okay? It is at a single point, it is a region only. So single point conditions are like this. First condition is, at that point function should be differentiable, and also we consider some neighborhood about this point. In that neighborhood also, at every other neighbor point, also the function should be differentiable only. Then only we can say function is analytic at that point z naught. It is about the analyticity or analytic function at a particular point only. Right? Next, singular point. Next definition is singular point. A function is not defined or not differentiable or not analytic if a function f of z is not defined, not differentiable, not analytic at any point z naught, then this point z naught is called singular point. At this point analytic, then analytic point only. Not analytic at this point, then the function has singular point at z naught only. You can say the function has singular point at z naught when function is not analytic only. So if we want to say that this point is singular point, we check the point, we check this point is singular point or not, like this only. We check the function is defined, not defined, or differentiable, not differentiable, analytic, not analytic only. If a function is not defined or not differentiable or not analytic at any point, then such a point is called singular point only. Now we'll discuss about the defined, not defined only. Let us consider the function f of z equal to z plus 3 by z minus 4 only. At z equal to 3, f of 3 equal to, at z equal to 3, f of 3 equal to 3 plus 3 6 by 3 minus 4, that is minus 6. Next, at z equal to 5, f of 5 equal to 5 plus 3 by 5 minus 4, 5 plus 3 8. At z equal to 4, f of 4 equal to 4 plus 3 7, 7 by 0, something by 0 is infinite. Now these are the function values at the values of z on. At z equal to 3, the function has finite value. At z equal to 5, the function has finite value. At z equal to 4, the function has infinite value only. At any point of z, the function has finite value, we can say that function is defined at that point. If a function has infinite value at any point, then at that point we can say function is not defined only. So at 3 and 5, the function is having finite value. That is why we can say the function is defined at 3, 5. At 4, the function has infinite value. Therefore, we can say the function is not defined at this point 4 only, right? So here, this function is not defined at z equal to 4. Therefore, 4 is a singular point of this function. What have you written here? If a function is not defined, not differentiable, or not analytic at any point, such a point is called singular point only. So here, this function is not defined at 4. That is why this point is a singular point of this function, or we said this function has singular point at z equal to 4 only. Or other way, we can say it is in the form of something by something only. For the existence of this ratio, the denominator part must be not equal to 0. But here denominator is 0 only for z equal to 4 only. So this whole function becomes infinite only at z equal to 4. That is why this function is not defined at 4, and this function is having singular point to 4 only. Okay? Or if we take another example, f of z equal to under root of z minus 8. Now we check this function is defined or not only. For all values of z, this will give finite value only. So we can say this function is defined for all values of z. If it is defined for all values of z, we can check the function is differentiable or not only. Now, in easy way to check the differentiability of this function, we take the derivative of this function, f dash z of this equal to, just like root x derivative. The root x derivative is 1 by 2 root x. Like that, the derivative of this is 1 by 2 into root of z minus 8. Now, this function is in the form of something by something only. The function is in the form of something by something like this only. But this is not defined at z equal to 8. When it is not defined at z equal to 8 means this is not possible at 8. It is not possible means derivative of this function not possible. That is, derivative does not exist at 8. At 8, this is not defined. So this does not exist at 8. This does not exist at 8 means the function is not differentiable at 8. When function is not differentiable at 8 means the function is having singular point. So if a function is not defined or the function is not differentiable at any point, then such a point is called singular point. Okay? Not differentiable, then not analytic. Not analytic means the point is singular point only. Okay? Not defined, not differentiable, not analytic at any point. Then such a point is called singular point only. So here in the first example, the function is not defined. Therefore, it is a singular point. In the second example, function is defined for all, but the function is not differentiable at 8. Therefore, 8 is a singular point of this function only. So this is about the singular point only. Neighborhood of a point means collection of all its neighbor points within the same distance in all directions only. Next, analytic function means two conditions. One is at a point z0 derivative exists or not, we check it. Derivative exists, then we consider its neighborhood, some neighborhood only. Corresponding to one point, we can get many neighborhoods only, depending on the distance only. Let us consider some neighborhood. In that some neighborhood, at every other point also, the derivative exists or not, check it only. So if a function is differentiable at a point z0 and also differentiable at every other point in the neighborhood of this point, then the function is analytic only. Next, a singular point. Not defined, not differentiable, not analytic at any point. Such a point is called singular point. Okay. Next, entire function. Next definition is entire function. Entire means all, everywhere only. So at every point in the whole complex plane, at every point in the whole complex plane, the function is differentiable. At every point in the whole complex plane, the function is differentiable or analytic. Then such a function is called entire function, right? So these are the some definitions: neighborhood of a point, analytic function at a particular point, next singular point, entire function. Now after this, we consider some examples and we check how to check the function is differentiable or not. But checking the differentiability by definition is not an easy, because correcting many points at a some point neighborhood means not an easy. That is why we consider one theorem. That theorem provides the sufficient conditions for testing the differentiability only. There are two conditions. Now this theorem provides us the two conditions for testing the differentiability at a particular point only. According to this theorem, for a function w equal to f of z equal to u plus I v, or u of x comma y, v of x comma y only. For this complex function, we check the two equations, ux equal to vy or not and vx equal to minus uy or not at a point z0. These two equations satisfy at a point z0. Then we check the next condition, that is continuity of u, v, ux, uy, vx, vy. Continuity of these functions at a particular point z0. So these two conditions satisfy at a single point. Then we can say that the function is differentiable at that point only. Here, the two equations are called Cauchy-Riemann equations or CR equations only. These two equations are called Cauchy-Riemann equations or CR equations only. So for this given complex function, the two CR equations satisfy at a point z0, and also all these six functions, 1, 2, 3, 4, 5, 6 functions are continuous at a point z0. Then we can say function is differentiable at a particular point z0. So at a point, these two satisfy, function is differentiable only. So this theorem provides us for testing the differentiability only. The theorem provides us the two conditions for testing the differentiability only. So according to this theorem, we can check the differentiability. Once the function is differentiable at a single point, we consider some neighborhood. In that neighborhood also, at every other neighbor point also, the function is differentiable or not, check it only. In the neighborhood also, at every other point differentiable, we can say function is analytic at that point only, right? Now this is the theorem only. The two equations satisfy for a complex function at a point, and the functions u, v, ux, uy, vx, vy are continuous at point z0, then the function is differentiable at the point. Once derivative exists, we can have the derivative of that function using this formula also, f dash z equal to ux minus I uy. Okay. This is the theorem only. That is, for a given complex function, f of z equal to u plus iv. First, we try to find the real and imaginary parts of this function. Next, we find the first order partial derivatives ux, uy, and then check the two CR equations ux equal to vy and vx equal to minus uy. We check these two CR equations satisfy or not. If these two satisfy, we can check the continuity of the six functions u, v, ux, uy, vx, and vy. If these conditions satisfy at a single point, we can say that at that point the function is differentiable only. Once it is differentiable at that point, we can check the analyticity condition. That is, in the neighborhood of that point z0, at every other neighbor point also, the same condition satisfy or not, we check it on. The same condition satisfy in the neighborhood also at every other point, then the function will be analytic at a point z0. Okay. So just we follow this. Here, the ux means dou by dou x of u of x comma y only. Similarly, uy is the dou by dou y of u of x comma y only. Next, vx means dou by dou y, dou by dou x of v of x comma y. Similarly, vy is the dou by dou y of v of x comma y. The real and imagined parts of the complex function. U is the real part of this complex function, v is the imagined part of this complex function. These two are the real and imagined parts of this complex function are functions of two real variables. Because of two real variable functions or more than one variable function, their derivatives are partial derivatives only. So first find out the u and v, next find the first order derivatives. After that, check the CR equation satisfy or not satisfy, we check the continuity of these only. All these satisfy at a single point. At that point, we can set function is differentiable. Once differentiable, we can check the next condition, further condition. What is the further condition? In the neighborhood of this also, at every other neighbor point of the same point, at every neighbor point of this point, that is all surrounding points. Also, the function is differentiable. We can set function is analytic at that point. Okay. This is a method of checking the differentiability only. Now, by taking the functions, some functions, I will show you how to check the function is differentiable or not, how to check the function is analytic or not at a particular point. So let us consider the function. The first one is w equal to f of z equal to e power x into cos y plus I into e power x into sin y, and the point is x comma y equal to 1 comma 0. Let us consider this function along with the point, and if you are asked to check this function is differentiable or not at this point, we should find the real and imaginary parts of this. After that, we check the CR equations conditions or CR equations, and after that we can check the continuity conditions only. That is, just we follow this. If you want to check the differentiability for any function at a single point, we follow this. First find u and v, next find the derivatives, after that verify these conditions only. Okay. First, let us find the real and imaginary parts of this complex function. Let w equal to f of z equal to e power x into cos y plus I into e power x into sine y, since it is in the form of the general function f of z equal to u plus I v only. Comparing this given function with the general function, we can get the real and imaginary parts of this function. Then u equal to e power x into cos y and v equal to e power x into sine y. Up to here, finding the real and imaginary parts is completed. Next, we find the first order partial derivatives. Ux equal to, that is dou u by dou x. Differentiate u partially with respect to x only. When you differentiate the function partially with respect to one variable x, we treat other variable y as constant only. So y is constant, cos y is constant, just derivative of e power x is e power x, e power x cos y, comma, u y equal to dou u by dou y equal to derivative of this function partially with respect to y. While differentiating the function with respect to y, we treat other variable x as constant only. So e power x is constant, cos derivative is minus sine, minus e power x into sine y. Next, Vx equal to dou v by dou x. V with respect to x, the same function, because this is constant, e power x derivative is e power x into sine y, and Vy equal to dou v by dou y equal to. We are differentiating with respect to y partially, so we treat other variable x as constant, e power x is constant, it remains same, and the derivative of sine is cos. So up to here we know the first four partial derivatives of u and v with respect to both variables x and y only. Next, we need to check the differentiability at this point. That is why we need to check the CR equation satisfy or not at this point. That is why first we try to find out all these derivatives at a particular point x comma y equal to 1 comma 0 only. At x comma y equal to 1 comma 0, we find all these only. Ux at this point. That is substitute x equal to 1, y equal to 0, cos 0, 1, e power 1, that is e. Next, uy. Uy at this point 1 comma 0, sine 0, 0. Next, Vx at this point. Substitute x equal to 1, y equal to 0, sine 0, 0, e power 1, 1, that is e. X equal to 1, e power 1, e. Next, v with respect to y. V with respect to y. At 1 comma 0, x equal to 1, e power 1, e, cos 0, 1. So this is e. Now we have these derivatives at a particular point 1 comma 0 only. At this point, we check the CR equation satisfy or not. The first CR equation is ux equal to vy or not. Here, ux equal to vy or not, check it only. Ux is e, vy, that's it. Vx is 0, this is 0. Ux equal to e and vy is e, these two are same. So here ux equal to vy at this point and vx equal to minus uy, because both are same 0, 0. So this equation will satisfy at 1 comma 0. So both CR equations are satisfied at 1 comma 0 only. Once the CR equation satisfy at a point, then we can go to the second condition, continuity of the six functions. Continuity of the six functions only. What are the six functions? U, V, Ux, Uy, Vx, Vy. Here, U is the real part of complex function, V is the imaginary part of complex function. That is, U is the real function, V is also real function, but it is a function of two variables x and y. It is a function of two variables x and y. Their derivatives are also real functions only. So checking the continuity of these functions, checking the continuity of these functions are the same as checking the continuity of real functions only. Already we know the method of checking the continuity of real functions only. Or we can use the some standard functions. With the help of the some standard real functions also directly we can set function is continuous or not. There are some real standard functions. I will show you the real standard functions. Now these are the some standard real functions only. Why the standard real functions? Why standard functions means they are defined at every point, they are continuous at every point, they are differentiable at every point, they are also integrable also at every point. We have these functions only: exponential, sine trigonometric, cos trigonometric, sine hyperbolic, cos hyperbolic, and every polynomial of this form. These six functions are at every point defined, at every point continuous, at every point differentiable, at every point integrable. So these are the standard functions only. Once you know the two functions continuity, once you know the continuity of these two functions, we can say that their sum is continuous or not, difference is continuous or not, product is continuous or not, division is also continuous or not only. When these two are continuous, the sum of the two continuous is also continuous, the product of two continuous is also continuous, the difference of two continuous is also continuous, the division of these two is also continuous with the condition the denominator part must be not equal to 0 only. When two functions are continuous, their sum is continuous, difference is continuous, product is continuous, division is also continuous when denominator is not equal to 0 only. This is the next result only, right? When two are continuous, differentiable, their sum, difference, product, division is also continuous and also differentiable only. So with the help of these standard functions and using this result, we can say directly the function is continuous only when the given function contains one of these standard functions only. Now here we have the standard functions only. Exponential is standard function, cos trigonometric is standard function, sine trigonometric is standard function. So with the help of that, the real standard functions, directly we can check the continuity only. We know that e power x is continuous at every point. Because of the continuous at every point, at a particular point also continuous only. At every point continuous means you take any particular point, at that particular point also it will be continuous only. Cos y is known that continuous at every point. Whenever at every point it is continuous, at a particular point also continuous only. Sin y is also continuous at every point, means at a particular point also continuous only. So exponential is continuous, cos is continuous, product of these two is also continuous only. Continuous, product of these two is also continuous only. Next, continuous, product is continuous, continuous, product is continuous, continuous, product of two functions, continuous is also continuous, continuous function, product of these two is also continuous only. So all these are continuous at every point. Because of the continuity at every point, you take any particular point, at that particular point also the function will be continuous only. But we are checking the continuity only a single point only. Already we have shown that these are continuous at every point. So at this particular point also continuous only. And also u, v, ux, uy, vx, vy are continuous. Continuous at 1, 0. Continuous at 1, 0. The two CR equations are satisfied at a point 1, 0, and at that 1, 0, all the six functions are continuous only. So when these conditions satisfy at a single point, we can set function is differentiable only. We can set function is differentiable. Therefore, f of z equal to e power x into cos y plus I into e power x into sin y is differentiable at 1 comma 0. Differentiable at 1 comma 0. Once you know that differentiable at a point 1 comma 0, we can check the analyticity at this point. So up to here we know that this function is differentiable at this point. Once differentiable, we consider some neighborhood of this point. It is 1 comma 0. Y coordinate is 0. When y coordinate is 0, the point y coordinate is 0 means this point lies on x-axis, and also x coordinate is positive. When x coordinate is positive, this lies on positive x-axis only. So 1 comma 0, this is the point. Now at this point we consider some neighborhood. In general, neighborhood means we take a very small distance only. But appears to be it is big, but we take the in general neighborhood means we take a small distance only. In this neighborhood also, at every other point also, the function is differentiable or not, check it only. Differentiability, we follow the same method only. We take this point, at this point, again we follow the previous method. We take this point, and we follow the same method. At this point also we check the differentiability. At this point also we check the differentiability like this. Instead of collecting all these points, we take some general point a comma b. At x comma y equal to a comma b. We take the general point of this region, and at this point we find the ux, uy, vx, vy only. Now what is the ux? Ux is this. At a comma b, the function is e power a into cos b only. E power a into cos b. And ux, next vy, at a comma b, e power a cos b only. These two will be same at that point a comma b only. Next, at a comma b, these two same or not, we check it only. Same and also minus. So the CR equations are satisfied. At this point, general point a comma b in the region, the two CR equations will satisfy only. Ux equal to Vy, Vx equal to minus Uy only. At every other point also, the equations are satisfied in the neighborhood of a point 1 comma 0 only. And all the functions are continuous at every point. So in this particular finite region also, at every point the functions are continuous only. So the functions are continuous in the region, and also the CR equations are satisfied at every point in this region. That is why the function is analytic at this point 1 comma 0 only. So f of z equal to u plus iv is analytic function at 1 comma 0, because the function is differentiable at 1 comma 0 and also differentiable at every other neighbor point in the neighborhood of this point. Function is not only differentiable at 1 comma 0, also differentiable at every other neighbor point in the neighborhood of this point 1 comma 0 only. That is why we say that function is analytic at this point. Like this we can check the differentiability and analyticity only. Just we go back. It is the function given along with the point. To check the differentiability, just we follow this method. Once it is differentiable at a point, then we can check the analyticity like this. We consider neighborhood. In that neighborhood also, at every other point, the function is differentiable or not, we check it only. It is a method of checking the differentiability for a given function at a particular point. It is a method of checking the analyticity for a given function at a particular point only. Now let us consider another example. The function f of z equal to x square plus y square, and the point x comma y equal to 0 comma 0. Function along with the point. Now first we need to check the differentiability of this function. Once it is differentiable at this point, then we consider neighborhood of this point. In that neighborhood also at every other point differentiable or not. To follow our method or theorem, we require the u and v of this function, that is real and imaginary parts of this function. Given f of z equal to x square plus y square. In this no imaginary part, we have just real part. So let us write this as I into 0 and compare this with the general function w equal to f of z equal to u plus I v only. Comparing the given with the general function, we can get the u and v only, which implies u equal to x square plus y square and v equal to 0. Let us find the derivatives of this function. Ux equal to 2x, uy equal to 2y, vx equal to 0, vy equal to 0. But here we are asked to check the differentiability at a point 0 comma 0 only. Now let us find all these derivatives at a point 0 comma 0 only. At x comma y equal to 0 comma 0 only. Substitute x equal to 0, y equal to 0 in the derivatives and find out the values. Ux at this point is 2 into 0, 0. At y equal to 0, this is 0. These two are already zeros. Now we have the derivative values at a particular point. So we check the CR equation satisfy or not. Here ux equal to vy and vx equal to minus uy. The two CR equations are satisfied at 0 comma 0. Once the CR equation satisfy at 0 comma 0, we can check the continuity of all the 6 functions. At the point all the 6 functions continuous, then we can say function will be differentiable only. Now to check the continuity of these functions, we check whether all these functions are standard functions or not. What are our standard functions? Exponential, sine trigonometric, cos trigonometric, sine hyperbolic, cos hyperbolic, and polynomial. The general form of the polynomial is a0 plus a1x plus a2x square plus and so on plus an x power n, and this n should be positive integer or natural number only. The power of the variable should be positive integer or natural number only. Then only this expression will be polynomial expression or polynomial function in variable x only. Okay. In this, x square is the second term in the polynomial only. So polynomial is continuous at every point. Y square is also in the form of like this. In place of x, y only. It is a polynomial, continuous. Continuous, continuous. Sum of the two continuous is also continuous only. Next, 0. 0 is a constant polynomial, only a0 term only. 0 is a constant term, a0 polynomial. It is also continuous. Every constant is a constant polynomial. This is present, rest of the terms are not present only. So constant is constant polynomial, it is continuous. 2x is a second term in the polynomial, it is continuous. 2y is the second term in the polynomial. 0 is a constant term. 0 is a constant term. So all these functions are continuous only. U, v, ux, uy, vx, vy, all these are continuous at every point because they are standard functions only. When they are continuous at every point means at a particular point also continuous only. Our particular point is 0, 0 only. And u, comma, v, ux, uy, vx, vy are continuous at 0, 0. So both conditions, the CR equations are satisfied at a point and the functions are continuous at a point, then we can say function is differentiable at a point 0, 0 only. Therefore, f of z equal to x square plus y square is differentiable at 0, 0. Right? Like this, first find the real and imaginary parts. Next, find the first order partial derivatives. To check the differentiability at this point, find all the derivatives. After that, verify the CR equations. Ux equal to Vy or not, Vx equal to minus Uy or not at this point. But at this point, 0, 0, both are satisfied only. These two are equal, satisfied. So when these two satisfy, then we check the continuity of the 6 functions. Continuity of the 6 functions. So finally, the two conditions are satisfied at a single point. Therefore, we can say function is differentiable only. Once it is differentiable, we can check the analyticity. Suppose if this is not differentiable, we can stop here. Not differentiable means not analytic also. But here it is differentiable. When it is differentiable, we can check the analyticity only. Now to check the analyticity for this function, f of z equal to x square plus y square at a point 0, 0. Up to here we have shown that the function is differentiable only. Once it is differentiable, we consider neighborhood of this point. This point is the origin 0, 0 only. Now about this point, we consider some neighborhood. Neighborhood is plane region, this circular region, circular plane region. This plane region contains many points only. Let us consider some general point a comma b only. Consider general point a comma b. X comma y equal to a comma b only. Now at this point, we find the derivatives. Ux equal to 2x. At this point is 2a. Next, uy is 2y. At this point is 2b. Next, vx is 0. At this point, vy is 0 at this point. Now, for this function, these are the first order partial derivatives at a general point a comma b in that region. Now here these two are same. In this region, the second CR equation Vx equal to minus Vx equal to Ux equal to Vy. Ux equal to Vy. It is not satisfied. That's all. You take any general point in that region, at that general point, we can get the derivatives like this. But if you observe the derivatives, the CR equation will not satisfy at a point a comma b only. Next, in the same way, other equation also. Vx is 0 and uy is 2b, both are not same. First of all, any one of the equation fails, we can stop here. Now from this we can say the function is differentiable at a point origin, but not differentiable at any other point in this region only. We can set here these two will be same. 2a equal to 0 only for a equal to 0 only. These two will be same. These two will be same only at a equal to 0 only. And these two will be same only at b equal to 0. Finally, we can set the CR equations will satisfy only at a point 0, comma 0 only, not at any other point. Not at this point, not at this point, not at this point only. The CR equation will satisfy only at a point origin only. That is why we can set function is differentiable only at origin, not differentiable at any other point. Because of this, not analytic at any point only. So it is differentiable only at one point origin and not differentiable at any other point only. That is, it is nowhere analytic only. Like this, we can check the differentiability, analyticity for a function at a single point only. Similarly, we can show that f of z equal to z bar. It is not differentiable at any point and not analytic at any point. Just like above, we can set functions nowhere differentiable, nowhere analytic. Very first example is everywhere differentiable, everywhere analytic only. But second example is differentiable only at one point origin 0, 0 and not analytic at any point only. But it is not differentiable, not analytic at any point only. Okay. Like this, we can check the differentiability, analyticity only. Now, for some functions, without using this CR equations method, directly we can set analytic only with the help of some standard functions. Like the real standard functions, we have the standard complex functions only. Now, these are the standard complex functions only. Whatever we have the real standard functions, we have the same standard complex functions only. The only difference is variable only. E power az, sin az, cos az, sin haz, cos haz, every polynomial of this form. The condition for this is this power of the variable should be from natural number or positive integer only. These 6 functions are at every point defined, at every point continuous, at every point differentiable, at every point analytic only. That is why we have taken these as a standard functions only. And if you are given some function, and if you are asked to check the differentiability or analyticity of that function, first we check that given function is in the form of any one of these or not. If you are given the function and if it is in the form of one of these, directly we can set differentiable, directly we can set analytic only. Otherwise, we follow that method. Suppose when two functions are analytic, their sum is analytic, difference is analytic, product is analytic, next the division is also analytic. But the condition for this is the denominator part must be not equal to 0. When this is not equal to 0, the ratio is also analytic only. If you know that these two are analytic, the sum is analytic, difference is analytic, product is analytic, and division is also analytic only. These are the results only. So using these standard functions, with the help of this, directly we can set function is analytic only. Let us consider examples for this. Suppose if you are given the function like this, f of z equal to e power z plus cos z plus z square, like this. If you are given some complex function like this, and if you are asked to check the analyticity of this, first we check whether it is a standard function or not. First of all, it is a sum of the 3 functions, 1, 2, 3. In the sum of 3 functions, every one is analytic. The total function or total sum will be analytic function only. So we check the one by one. E power z is a standard function or not. Very first standard function is exponential only. It is in the form of e power az. So it is an analytic function at every point. Cos trigonometric is also analytic at every point. Now it is a polynomial. The general form of the polynomial is a0 plus a1 z plus a2 z square plus and so on plus a n z power n only. Now this is a third term in the polynomial only. We know that every polynomial is analytic at every point. Cos trigonometry is analytic at every point. It is also analytic at every point. The sum of the 3 analytic is also analytic at every point. So this function is everywhere analytic only. Without using CR equations, directly we can set here the function is analytic only because of the standard complex functions and the results only. So it is analytic at every point. Analytic function. Next, the function is given like this: f of z equal to z cube plus z bar. Again, sum of the two functions. In the sum of the two functions, every function is analytic. The total sum will be analytic. In the sum of the two functions, any one is not analytic. The sum will not be analytic only. Now let us look at each function. Z cube is a polynomial. It is the fourth term in the polynomial. It is analytic at every point. And z bar. This z bar is not analytic. The z bar is not analytic. Just now we have shown how to check the function is analytic or not, differentiable or not only. And this z bar is nowhere differentiable, nowhere analytic. That is not differentiable at any point, not analytic at any point. So this z bar is not analytic at any point. It is analytic at every point. Finally, sum is not analytic only. Not analytic function. So it is analytic because every term is analytic function, sum is also analytic. And in this sum of the two functions, this is analytic, it is not analytic. So therefore, the sum is not analytic only. A third example, f of z equal to z into z bar, or to take another function, e power z into z bar. Product of two functions. E power z is analytic at every point, but z bar is not analytic at any point. So product is not analytic. Product is not analytic. Next, last example, f of z equal to e power z divided by z plus 4. This function is in the form of something by something only. So we take this as one function, this as one function. Already we know that when two functions are analytic, the sum is analytic, difference is analytic, product is analytic, division is also analytic only. When g not equal to 0 with this condition. So using this, we can say that analytic or not. Only e power z is analytic at every point. Only z plus 4 polynomial a0 plus a1z, it is also analytic. It is also analytic. Independently, these two are analytic only. And when you consider the total function is also analytic when g, this z plus 4 not equal to 0 only. Right? So analytic, the total function will be analytic when this is not equal to 0 only. So from this we can say it is analytic at every point except minus 4 only, like this. So without using CR equations or without using theorem also, directly we can set function is analytic or not, like this only. Whenever the function is in the form of standard functions or combinations of standard functions, like this only, right? This is the method of checking the differentiability and analyticity only. So with this, we stop the today's session and we continue this tomorrow only, the continuation of this topic only.